Hello, everyone, and thank you all for joining in EMWorks webinar series. In today's webinar, we will cover design and analysis of a three-phase induction motor using magnetic equivalence circuit method and finite element method. In this webinar, we will discuss different characteristics of an induction motor and how we can calculate them using the magnetic equivalence circuit method and finite element method. What are advantages and disadvantages of these two methods? So first of all, let's have a look on the webinar's content. We will review the properties of the magnetic equivalence circuit method. Then we will discuss its advantages and disadvantages in compared with the finite element method. Then we will discuss the static simulation of induction motor, then dynamic simulation, and torque speed curve calculation of the motor, and then calculation of performance curves and map curves like efficiency map, iron loss map, and copper loss map, right? The motor presented in this webinar is a 1 HP induction motor, and the number of poles is equal to 4. So, what is the magnetic equivalence circuit method? Magnetic equivalent circuit method is one of the numerical methods employed for the transient analysis of electric machines, but we can use it for both magnetostatic simulations and transient simulations, right? The magnetic equivalence circuit method is essentially a finite element method, right? In the finite element method, we discretize the solution region using mesh elements, right? And then we solve the field equations on the solution mesh and calculate the magnetic vector potential, right? But in the magnetic equivalence circuit method, the number of mesh elements is lower, right? So, however, the magnetic equivalence circuit method is similar to the finite element method, but we have two important differences. The first one is the lower number of elements, and the second one is directional flux, right? So, in the finite element method, if we want to calculate the value of flux density in different locations of the motor with a good resolution, we should increase number of mesh elements, and this will increase the solution time, right? But in the magnetic equivalence circuit, the number of elements is low, and we can solve the system of equations faster with a lower resolution, with a lower precision. But the results are still good enough. I will explain. The second difference is the directional flux, right? This picture shows the magnetic equivalence circuit of induction motor. Here you can see the reluctances or permeances, right? We have nonlinear permeance and we have linear permeances as a function of the rotor position here between stator and rotor teeth. So when we draw this equivalent circuit, we should know the direction of the flux, right? We should have a good indication about the flux direction. in each element. But in the finite element method, the direction of flux is arbitrary and you don't have to specify it. Actually, you calculate the flux density after solving the magnetic vector potential equation. So the finite element method is a general purpose method, but the magnetic equivalence circuit is not a general purpose method. And for each specific motor type, you have to develop the corresponding equivalence circuit and solve it, right? So we have these two important differences. So these differences between the magnetic equivalence circuit method and finite element method cause some advantages and disadvantages, right? So here you can see advantages of the magnetic equivalence circuit method. The solution time is low and the simulation is fast. For example, if you want to do dynamic simulation, right? So because number of mesh elements, number of circuit elements is low, the dimensions of the solution matrix is not too high and you can solve it in a short time, and that is good property when we want to do dynamic simulations, right? Because in dynamic simulations, if we want to get good waveforms, we should use a low time step, right? The time step should be fine enough. So this property makes the magnetic equivalence circuit good for optimization and good for sensitivity analysis, right? Because in sensitivity analysis, we change the dimensions of the motor, either mechanical parameters or electrical parameters, right? We change and we want to capture the dynamic performance of the motor. So the magnetic equivalence circuit is an effective way to do sensitivity analysis and use it for optimization, right? So, however, results are not precise as the finite element method, but we can use this method as a pre-design method in the pre-design stage, and then after getting a good solution, we can tune the design using the finite element analysis. So we have two disadvantages. The modeling time is high, right? So as I explained in the previous slide, for each motor type, you have to develop its corresponding circuit, right? So the modeling time is high, and when you change the geometry of the rotor or a stator lamination, you should modify the equivalence circuit, right? Another disadvantage of the magnetic equivalence circuit method is its complexity for implementation for complex geometries, right? For example, synchronous reluctance motor. In the synchronous reluctance motor, the rotor's geometry is complex and the prediction of the magnetic flux lines through the flux barriers is complex. So the implementation of this method for complex geometries is time consuming because it's hard to find a good equivalence circuit method to capture good results, right? When the flux line pattern is complex. But this situation is not for induction motor. For the induction motor, the geometry is regular and the flux lines pattern is regular, and this equivalence circuit is good for analyzing the induction motor, right? Because the prediction of the flux lines inside rotor yoke, stator yoke, rotor teeth, and stator teeth is not too complex. In compare with the magnetic equivalence circuit method, in the finite element method, the modeling time is low, right? Because the finite element method is a general purpose method. You can draw any geometry and analyze it, right? So no matter what is the geometry of the motor, you generate the geometry, apply proper boundary conditions, and solve the problem. So, but using finite element analysis for optimization is complex, right? Because for optimization purposes, we need to do dynamic simulations. And when we want to consider a fine time step, the simulation time is high, and consequently, it's hard to implement finite element method for optimization or sensitivity analysis purposes. So a combination of these two methods is a good solution for design of an electric motor, right? You can use magnetic equivalence circuit for motor sizing and pre-optimizations, and then using the finite element method for design tuning, right? And double checking the results generated by the magnetic equivalence circuit method. So let's see results generated by these two methods for the induction motor, right? Our case in this webinar. So you can see here the motor structure. We have a stator core, a stator winding. A stator core is slotted, and we have distributed winding. Here we have rotor cage and the rotor core. So for analyzing induction motor, we need to do different simulation types. And in EMWorks 2D, you can do different analysis types in one place when you generate the motor geometry easily inside the SolidWorks. You can define different analysis types. Here I defined the steady state, magnetic, loading, and map curves designs. So you can do different analysis types under one project name. That is pretty good because you update geometry, and the geometry will be updated for all design types, and you don't have to create different geometries for different analyses. And this is a good feature that you can do your different analysis types in one place. So I used EMWorks 2D for the first analysis type, that is the magnetic loading. You can see the flux density pattern. And in the magnetic loading analysis, we excite the phase A, phase B, and phase C of the stator winding to calculate the radial component of flux density in the middle of air gap, right? So you can see here the flux density waveform and its fundamental harmonic, right? So because I use the fine mesh, you can see the flux density waveform with a good resolution here, and you can see the effect of stator and rotor teeth, right? So in the magnetic equivalence circuit method, we should use a number of elements, permeances for rotor uke, rotor teeth, stator teeth, and stator uke, and also permeances between rotor teeth and stator teeth to find the value of flux density in each mesh element, right? Or in each location of the motor. So this figure is from this reference, And you can see a portion of induction motor magnetic equivalent circuit, right? Here is the equivalent permeance or equivalent reluctance of the stator tooth. And this is for a stator duke, a stator tooth. Also, we have this reluctance for rotor duke, and this is for rotor tooth, rotor tooth. And also these two reluctances shows the leakage flux, right? This is the leakage flux for stator teeth, right? This leakage flux is between two stator teeth. And also we have this leakage reluctance, right? Also, you can see this grid of permeances, right? Actually, between each stator tooth and rotor tooth, we have one reluctance. Actually, we have Ns times Nr, right? Reluctances. Ns is number of stator slots and Nr is number of rotor slots, right? And these air gap reluctances are functions of the rotor position, right? Here you can see the relative position between one stator and one rotor tooth. So generally, we have three types of reluctances. Nonlinear reluctances due to the nonlinear property of the material. Linear reluctances, constant reluctances like this one, and nonlinear reluctances due to geometrical parameters, for example, the rotor position, right? So in this equivalent circuit, the purpose is finding the magnetic potential of the circuit nodes, right? U1, U2, U3, and U4. You can see these circuit nodes, right? So our aim is finding the magnetic potential of these nodes, right? So when we know the magnetic potential, we can calculate the magnetomotive force drop, and finally we can calculate the flux, and then we can calculate the flux density, right? So yes, in the finite element method, we excite the stator winding, and then we can pick up the value of flux density in each location of the stator and rotor cores, right? But in the equivalent circuit method, we calculate the average value of flux density in each stator tooth or rotor tooth, right? When we solve this equivalent circuit. So this is one difference, right? We are working with the average values, right? If we increase number of elements in the equivalent circuit method, we can get a better resolution. But consider that our purpose is not to use a complex circuit, right? Because our aim is to have a simple solution for dynamic simulation of the induction motor. So this equivalent circuit is good enough for these purposes. The next simulation type is the dynamic simulation. In the dynamic simulation, we define a motion and we apply torque and we do real-time simulation, right? We do voltage fed simulation and we solve the circuit equations coupled with the field equations to find the torque, speed, currents, and so on, right? So dynamic simulation using the finite element method is time consuming because when we do voltage fed simulation, we should couple the field and circuit equations completely. So the solution process is time consuming. In the magnetic equivalent circuit method, we can use the energy balance equation to find the value of electric torque in each time step. Here you can see the equation. for calculation of the force, and we have similar equation for the calculation of the torque, right? Actually, the value of permeances that are a function of rotor position are in this equation, because for the rest of reluctances, we don't have any value for this derivative, and this derivative will be zero for these reluctances, right? So the value of these reluctances between rotor and the stator teeth will be used for calculation of the torque. And in the magnetic equivalent circuit, also we can solve the circuit equations and field equations, right, to analyze the dynamic behavior of the motor. So the next characteristic of the induction motor that is of interest is the torque speed curve, right? Our case study motor is a 4-pole motor and the synchronous speed is 1500 RPMs. You can see the synchronous speed here, maximum torque and a starting torque, right? This curve also shows the load torque equation, and these two curves shows the results generated by the finite element analysis and also magnetic equivalent circuit method. As you can see here, the results are close and we can use the equivalent circuit method effectively, right? I calculated the torque speed curve using EMWorks 2D by doing different transient simulations. Actually, for calculation of the torque speed curve, we need to do fixed speed simulations, and we should fix the rotor speed and do simulation with a good enough time step, right, to pass transients, and then calculate the average values, and then connecting the average values to draw this curve. So I did these simulations and I generated these results using the software, and then I used the Excel software to calculate average values, and then I calculated this torque speed curve. So here also you can see the graph for the zero speed, right? We should do simulation high enough to pass transients. So, but as you can see here, the results between the magnetic equivalent circuit and finite element method are close enough, right? For the magnetic equivalent circuit method, we can get a smoother curve, right? Because this is analytic method and we used a smooth functions, right, for these permeances, and the curve is smooth, and this is for finite element method. Calculation of the torque speed curve using magnetic equivalent circuit method can be done in a logical time, right? So every single dynamic simulation using magnetic equivalent circuit method can be done below 1 minute, right? Even with a fine time step. But every single dynamic simulation using the finite element method will be time consuming. So this is why a combination of these two methods is good, right? We can use the equivalent circuit method in the pre-design stage, and finally verifying the results using the finite element method. Another advantage of the equivalent circuit method is for calculation of the performance curves of induction motor, right? This graph shows the torque speed curve of an induction motor, right? As you know, for induction motor, we have three regions: constant torque region, constant power region, and high speed region, right? So if we want to calculate this torque speed curve, for example, with the maximum torque per ampere strategy, we need to do a high number of dynamic simulations, right? Because at each speed, we should do a sweep over the rotor slip, and then we should find the corresponding maximum torque, right, in that slip sweep, right? So in each speed, we have to do several simulations. So, for example, if you want to calculate this graph for 100 speed points, in each speed points, if you want to do a sweep over 100 points for the slip, so 100 times 100 is the number of total dynamic simulations that we need to generate this graph, right? So using the finite element method is very time consuming, but here you can see this result that is generated by the solving of the magnetic equivalent circuit method, right? So you can use the equivalent circuit method to calculate this graph, and then for checking the correctness of the results, you can pick up some points and do corresponding finite element calculations, right? So this is a great advantage of the magnetic equivalent circuit method for calculation of this characteristic, right? And when you calculate this graph, you can use the similar logic and change the value of the amplitude of the stator current to calculate these performance curves. For example, torque versus the rotor speed, phase current versus the rotor speed, slip frequency, and so on, right? So this is also a good advantage of the equivalent circuit method, right? So yes, when we have this data, we can calculate copper loss map, iron loss map, and finally, we can calculate the efficiency map, right? So calculation of the copper loss map is straightforward because we know the value of stator resistances and rotor bar and rotor engine resistance. So when we know the value of currents, we can calculate copper losses. Also, because in the magnetic equivalent circuit method, we calculate the value of flux density in each rotor tooth, stator tooth, rotor yoke, and stator yoke elements, then we can use those numbers to calculate iron losses, right? And here you can see the iron loss map, right? So combining these two curves by knowing the value of torque and output power, we can calculate the efficiency map that you can see it here, right? So again, you can pick up some points and validate the result using the finite element method. Okay, so right, the aim in this webinar was the comparison between the equivalent circuit method and finite element method. And if you need any information about the calculations behind these results, you can contact us, right? And also you can check the MotorWizard, right? Software to know more information about using this kind of analysis methods, right? Implemented for analyzing all the induction motors. So thank you all for being in this webinar.